Well, the thing I only have very short time for the presentation, so I have decided to focus on the topic that is actually the topic for my visit to Korea this week. This is to discuss with the Korean headphone manufacturers a new ETSI standard for active noise control headphone testing. ETSI is European Telecommunications Standard Institute, and they write standards for telephones, telecommunications, and so on. And they have recently made an updated version of the ETSI standard for test method and performance requirements for active noise cancellation headset and other earphones. I will not go through the whole test procedure. We do have a webinar where one of my colleagues go through all of this, but I will focus on some of the things that are new in the ETSI standard. Basically, the acoustical test of active noise control, active noise cancellation headphones. There's a lot of electronic tests, microphone test and speaker test. But what I will focus on is the headphone, the insertion loss measurement, and the self noise, the hiss noise from the active noise cancellation theory. But in basic, we can say that an active noise cancellation headphone consists of a loudspeaker, some ANC circuit, and microphones, either feed forward microphones outside or feedback microphones inside, that try to regulate the noise field inside the headphone so that it is lower than without. What I will focus on here is a very small part of the full test of ANC headphones, the part with acoustical part of the part here with artificial ears and head simulators and microphones in order to test the acoustical performance of the ANC. If we look briefly at the three tests that are relevant here, it is insertion loss measurement and noise cancellation performance of the headphone. If we start with the insertion loss, we put the hats or the head and torso simulator in a test room, and we play noise around it. We first record the noise without the headphone on. Then we put the headphone on, and we record again the same signal. And the difference is the passive insertion loss of the headphone. Next, we turn on the active noise cancellation circuit, and we get a new level and measure this. That will give us the active noise cancellation. Second test is the self noise of the active noise cancellation circuit. If we have a totally quiet room, we put the headphones on and we record the background noise level. And then we turn on the active noise cancellation circuit. We will sometimes or often see a small change in level. That is a hiss noise from the active noise control feedback loop, something very low, but still there, and maybe important parameter. Now, in order to do the test here, we cannot use a test person in all. It has to be some objective measurement, and for this we use a head and torso simulator, basically a device that simulates the same shape as the human head, the same something that simulates the torso of the human body. And then inside the head we have the ear simulator with a microphone and an impedance simulation device, and outside we have the pinner. So to test the device, we could either put the headphone around the ear or inside the ear canal. And the important parameter for the ear simulator is the ability to record the sound pressure level as it would be in the human eardrum area. If we have a typical or a model of a human ear, we have the entrance to the ear canal here, and inside here we have the eardrum. We can make a model of this ear channel like this. We have the input plane here, and we have the eardrum here. Now we can simulate or measure the transfer impedance of the ear canal. That is the relationship between the input signal here, what the input signal will produce of pressure at the drum position. This gives us what we call the normalized transfer impedance, and this tells us something about how a noise signal from the input of the ear canal is transmitted into the to the eardrum, and from there, how do we perceive it, how loud it is. We can see at low frequency we have a good transmission. We get a lot of sound pressure at the eardrum position for a given input. Some area here we have a lower transmission, and then we have some resonances here. Now if we look at what the sound field looks like in the ear canal, these are the simulation of the sound pressure fluctuations inside the ear canal. At low frequencies here, this is around 100 and 200 hertz. We can see that the sound field or the pressure in the ear canal is the same through the length of the ear canal. Down here, wavelength at 200 hertz, wavelength is around 1.5 meter. So the wavelength is very long compared to the dimension of the ear canal. So therefore, it's the same pressure throughout. We can also say that what determines the level of the transfer impedance is the volume of the ear canal. That is the determining factor here. Now, if we go to high frequencies up here at 5 kilohertz, we see that the pressure at the input of the ear is 180 degrees out of phase with the pressure at the eardrum position. This is the half wavelength resonance of the ear canal, corresponding to an ear canal of about 36 millimeter. But this is the resonance in the ear canal length here. We see some double frequency resonance. Okay, so, and here we have the crossover where the eardrum is getting stiff. So But what we need to look at is another important factor for the ear coupler is the threshold or the microphone noise. Normally, a human ear can hear down to around 0 dB. And you remember, 0 dB is not zero noise. 0 dB is the limit of what the human ear can hear. But we can measure below that. And the problem is that a normal measurement microphone has a noise floor around up here. So we cannot measure with a normal microphone the same levels that we can, that humans can hear. And the microphone we have some thermal noise in the microphone, thermal noise in the preamplifier that adds up to this problem here, that if we measure this is the background noise level or the open ear noise. This is the passive noise insertion loss of an ANC. And when we start the active mode, we can see that we get about 20 dB reduction at low frequencies. But at high frequencies, we see that it's actually gives the same results whether we are using passive or active noise control. This is because this is actually just the self noise or the noise of the microphone itself. If we change it to a super low noise microphone in the coupler, we can see that we get the full measurement up at high frequency. We can see that the active noise control mode is actually generating extra noise compared to the passive mode. I have only very few, so we have to go a little fast here. But also what we can see is the background noise or the active noise cancellation headphones self noise. If we try to measure it with a standard microphone, we only measure the noise flow of the microphones. But if we use some extremely low noise microphones, we can see the red curve is in passive mode. We have low levels in the headphone. As we turn on the active noise control, the noise level in the ANC device goes up by something 10, 15 dB. And this will be an audible noise that you can hear in the ANC when you turn on the device. Another problem we face with ANC detection is that normal hats or head and torso simulators, they have a lot of transmission of noise through leakages, through vibration testing and so on. So in general, they can only test about 35 dB attenuation. And modern ANC devices, they have typically much better insertion loss than the test device itself. So we have to use some special optimized head and torso simulator which have an extremely high self-insertion loss, something up in the 17 and 80 dB. It's an ANSI standard that specifies this type of device. And with this, we can measure very high ANC performance. We can actually measure up to about 70 dB ANC performance. So as technique evolves, as ANC headphones becomes better and better, we need more and more advanced test systems here. So very short presentations of what we have of new developments in active noise cancellation testing, how the increased performance of the active noise cancellation headphones drives the need for better and more accurate test equipment. Thank you.